So that's good to know how to like.
All right. Hello, everyone. Howdy, howdy. It's our last. It's not our last class. It's our last class of new content. Yay! Glad y'all are here to do a lab today. Yay! I don't know. You'll play around with light and thing. It'll be fine. It's a very straightforward. I say straightforward. Y'all will see it when we get to it. So a couple logistics things. Note card, you all get a 5x8 note card. I have some here. Just reminders, everyone, you only get the one 5x8 note card. All the test scores are posted, so that's done as well. Sometime either tonight or tomorrow, what I'll try to do as well is update your all's iClicker grades. And once I've done that, every grade will effectively be there, except there's one more quiz that opens up on light and stuff like that. But otherwise, pretty much all the grades will be there. You all can play around with the Excel spreadsheet to determine what you need to accomplish X grade. The spreadsheet is the best place for you to figure that out. I get a few questions like, hey, I have these grades. What might I need to do? It's just play with the spreadsheet. That's going to tell you based on your own grades and things. The final, I have made a draft of it. I reduced it slightly in length from 40 questions to 36. Not a big change. That was just to make it, if this was your only final that you had that day, I wouldn't be as concerned, but I know some of you might have 2 finals that day. So I don't want to really turn your brain into absolute mush. But at the same time, I got to test all the things and stuff like that. Heads up, there will be problems on here that are similar complexity to the free response. Maybe like 10% of them or something like that. 4 to 6 questions have multi-step processes to them. Good. Look at the free response from previous exams. Look at all that kind of stuff to make sure you're ready for that stuff. But otherwise, it's got a mixture of quick things and it's got a mixture of plugging in numbers and just doing it purely in variables. Only about 30 to 40% of them require you to use a calculator. So that's to also make things move a little bit quicker. And so I'm going to run that by. Again, at this point, I have a draft. I'm going to send it to the TAs in this class. They're going to look it over. I'm going to look it over at least 2 more times. Make sure there's no typos, all those things. Make sure it's representative. But rule of thumb, if you did well in test 1 and test 2, you should be capable of this. Just make sure you're warmed up on that. If you didn't do as well, make sure you learn the things that you didn't do well. Same with every class you ever take, right? All right, joke of the day.
Hello. How does a cucumber become a pickle? It goes through a jarring experience.
Yeah, it's good. All right, so we have barely anything left to get through. We got it's 15 slides, but a lot of this is not stuff I'm going to test you on. I'll tell you what stuff I'm not going to test you on. So just to recap, this entire PowerPoint slide, we talked about waves. Then we made them into electromagnetic waves. Then we talked about the energy stored in those waves. Then we talked about reflection. There won't actually be any questions about reflection on the test. They're a little too straightforward. But we talked about it because you should probably know that light reflects and how it reflects and all that jazz. This is the last thing I need to teach you. This and one more equation. This is called the index of refraction. This is a ratio of basically how fast light goes in a material compared to the speed of light in vacuum. So C is 3 times 10 to the 8. That is the fastest light can travel. In a material, it looks like light travels slower, and that's what this ratio is. Now, there's an asterisk here, because light technically always travels 3 times 10 to the 8, which is a wild idea. You're like, what do you mean that's a wild idea? That seems pretty obvious. I think I mentioned this to y'all before. Something crazy is like, say you're in a spaceship, and you're going half the speed of light, and you shine a flashlight on that spaceship. Normally, when you have 2 velocities, they just add together. If you're in a car going 60 miles per hour and you throw a ball 10 miles per hour, how fast is that ball going? 70. Light doesn't work that way. If you shine a flashlight on a ship, it's going the speed of light. Someone outside of it, how fast do they see the flashlight light? The speed of light. It's weird. Light always travels the speed of light. Weird things. Anywho. So I say that little asterisk here. Technically, light doesn't slow down. What's happening here is that there's electrons in it, and those electrons wiggle, and they make their own light, and the constructive and destructive interference from the original light and the light made by the electrons result in this looking like it's slower. So functionally, we just say it's slower, but realistically, it's just, I don't know. Physicists need to know that light's always 3 times 10 to the 8, and that doesn't change. Engineers, don't worry about it. All right, N equals, and yeah, so great. N equals C over V. V will always be smaller than C. Let's see if that made sense. According to what I just taught you, again, there's another asterisk here. What is the smallest value N can be? There are some materials that break this rule, but don't worry about this. Oh, thank you. Boom, posted. There is only one right answer here. And it's not a trick question, it's just what do you think? So what's our question?
Fastest you can do is C over C.
What's the fastest?
You get C slower.
Yeah.
The adjusted velocity is 0.
Yeah, what's the variable we use to represent that? Let's see.
Yeah.
So the smallest value for the base value of C theoretically, C divided by C is
What's not getting checked?
my speed is slower. It's not getting slower. What if my speed was C over 2?
It's like
have to write it out. It's D, so
there's no way you can.
replace B, C over 2. And the 2. So, as V goes down, so basically so if it's the same,
Well, I mean, the only that class will not be 1 unit. Yeah. Only the case when you yeah. I got no. I don't think you guys thought that. Yeah. I would have -6.
Oh, that might be. I'll double check.
All right, give y'all 10 more seconds.
They were asking about the grade for lab 1 and we're saying it's like not.
Yeah, it doesn't matter.
Doesn't matter.
No, it doesn't even count towards anything. Yep. All right, in 3, 2, 1. All right, so what's the smallest value n can be? This is where we're just going to look at our equation and play around with it. So n equals c over v. So we're going to do something called boundary condition. We're going to look at our boundaries. When v is really small, you know what? If this is not a possibility, but let's just say it. As v approaches 0, what does n approach? Infinity. So there is no limit to n. Now, realistically, no material makes light slow down this much. The largest values of n that you find are generally like 4 or 5, meaning that the velocity in that material is like 1/5, 1/4, yada yada. All right. So that's the minimum that the velocity could be. Again, it never reaches that, but whatever. What is the maximum that v can be? What is the speed limit of the universe? It is c. And as v approaches c, we get n equals c over c, which is you cannot get smaller than 1. If you get smaller than 1, what does that mean? You are traveling faster than the speed of light. And one of the rules of the universe, I don't make the rules, I just teach them to you, is you cannot go faster than the speed of light, as far as we currently understand things. That's where sci-fi comes in and all that jazz. FTL, faster than light, sci-fi. Yeah. So, it's 1. Now, there are some materials that break this rule. Light does not travel faster than the speed of light in those materials. It represents a different kind of velocity. You got to get more into the details of it. And these are like really weird materials. It's like helium doing weird things. I don't even remember. Check out the Wikipedia page. All right. Which, that's an interesting statement in and of itself. If you haven't realized this, if you go to Wikipedia for any physics topic, it tends to be very thorough. Like, I generally don't actually recommend Wikipedia pages for people for physics until they get to like their upper level physics courses, because that's how in depth they are. They're really good, but yeah, they're a lot. But they are really good if you want to learn more in depth about physics. Just be prepared that they get into the deep end of things. They're very thorough. It's really good. Yeah. All right. A plane infrared wave traveling through some transparent media is given by this equation: E naught sine 2 pi parentheses y over 5 times 10 to the minus 7 minus 3 times 10 to the 14t. Find the index of refractive index. Find the refractive index of this medium at that frequency, and find the vacuum wavelength. So what we're solving for is 2 things. First one, find n, given this wave. This wave, just to make sure we're clear, is not traveling at 3 times 10 to the 8. You need to first, in fact, the answer here is not the right answer. This is the velocity of the material. You need to figure that out. You actually need to solve for this velocity, and the answer will end up being, when you do it correctly, you'll find that n equals 2. Then the second question says, find the wavelength if this was in a vacuum, specifically if it was traveling the speed of light, and for that you'll need the frequency. I'm really focused on part A, though. Find the velocity. Can you read this equation and find the velocity? You will have to do some math. You will, may or may not want a calculator. Depends how good you are with scientific notation. So this is, again, can you read the wave equation? Hopefully I've stressed that that's an important skill.
Oh, the standard rate, yeah. I just thought
So many times at this point I do, but yeah, no, I don't have the words.
So many.
I only remember it today.
So many pieces of that.
I just remember the 2 pi over lambda when the x minus plus vt is pretty. That's actually why I wrote it that way. That's the easiest one to remember. You could do the kx minus omega t.
And you also remember K and omega.
But yeah, the k, then you have to remember k is 2 pi over lambda. Just like, I'll just remember the 2 pi over lambda.
Yeah.
That's new.
If you're stumped, write the general expression for the wave equation. The general one. Y x comma t equals yada yada yada.
What's the vacuum wavelength? N percentage one.
I might answer this vacuum wavelength. No, I think that's right. The vacuum wavelength basically means, so currently this wave is not traveling the speed of light. Yeah. If it was traveling the speed of light, what would actually happen? And the key there is that the frequency stays the same. The speed changes. The wavelength changes.
Yeah, I don't know if there's another way to do it besides figuring out putting it in because I know that this is the frequency of it. So if I solve for it this way, you just get the same thing. Which is interesting. Like this is the way like that's the frequency. I didn't know that. Like you
Well, it's because you're leaving lambda out, so
Right.
it's actually divided.
yeah. So I just multiplied it by that.
Sorry, our exams tomorrow.
So again, when I'm going around, I'm looking for, did you write or do you have the general wave equation written down? If not, good luck. This is very hard if you don't have that written down.
Yeah.
This makes them look like each other. That's all you got to do. Make them look like each other. Yeah. Yeah, so yeah, that's where I made it, and I updated it up here. Yeah. So that's the speed, and then you need to use that. Yeah. You're
Not yet. Divergence curls.
My professor is I signed up as only those who saw us in the gradients. My professor is holding us
So there it is. If you didn't have it already, this is what I kept saying a bunch of times. Make them look like each other now. Make this the one I gave you look like that one. Because then if you make it look like it, you can say what V is equal to. Make the equation I gave you. Either make one look like the other or vice versa. Make them look the same.
So, 3 tips.
Yes.
How much frequency give the third distribution is like stiffness of this key.
And then once you do, you'll see those back. But isn't
wavelength is different. Okay, so the frequency is the same. That's the same frequency, right? Like when waves go through medium
Not that bad.
frequency is the same. The velocity is vacuum. No, velocity is so the velocity is that when you're going through the material, right? What's the vacuum? The vacuum velocity.
Yeah.
I agree.
Yeah, just be honest. You're finding the vacuum is you're finding all of these when it's not. That's the same. So the wavelength is changed.
Honestly, I was pretty upset.
I think it might just be because that would change the wave equation. Yeah.
Oh yeah.
Oh, you're right. But what do you think? Because it's 11. So he's like, yeah, no, I'm getting a 0 for this last year. It's getting like a grade out.
All right. So again, the key here is, can you make them look the same? I keep saying it time and time again, and because that's what I'm going to do. So I'm going to take this function, and then I'm going to write the other one right next to it. This is how you do all of these problems. E naught times sine of 2 pi times, I'm going to put them right next to each other so that we can see that they don't look like each other. Okay, if you compare these two equations, great. Amplitude and E naught, those are the same thing. Awesome. Look at my next term, sine and sine. Awesome. After that, I have 2 pi over lambda, but the next one just says 2 pi. So that's not, if those are the same, then you'd have to say lambda is 1. May or may not be. Let's keep looking. The next thing I look at is this is an x by itself. X and y are interchangeable. That's just the direction you're traveling. In this case, the wave's traveling in the y, and the general one is traveling in the x. It doesn't really matter. Oh my gosh, this one's not by itself. Okay, how can I make them look the same? Get y by itself. How do you get y by itself? Pull that thing to the front. Pull that 5e to the minus 7 to the front. Now, if you pull it out of this parentheses, you better pull it from both terms. Do not just pull it from the one. You're not allowed to do that. You can't just take it. You got to follow algebra. So if you're going to pull out that 5e to the minus 7, you need to pull it out from both terms. So if you haven't done that yet, do that. E naught sine of 2 pi over 5e to the minus 7. Oh man, they're starting to look similar now. Times y, and I'm going to let you do the second term if you haven't done so already. This is the idea. Make them look the same so that way you can compare them and do things. Give y'all like a minute for that. Oh, yeah, it's one time. Oh, it's a blue box.
Oh, okay.
Yep, which are.
That's everything.
Sorry, you're not gonna. And there's no safety. Oh, there's a ladder.
I was like, wait, what?
Oh, no.
Ladders are good.
Yeah.
Never mind, you can't reach.
I think I can reach them.
They're the magic of technology. Yeah, I can kind of reach up there as well, but it gets a little hairy. All right. So if you pull it out of the bottom, that means this one's going to get multiplied by it. Great. Now that they look like each other, if I ask for wavelength, look, there's wavelength. Now you look at part B and say, that's not the answer. It's because it's different. Something. If you want velocity, that's the velocity. Make them look like each other. This is there is 3 questions on the final where I give you a wave equation and I say find something useful from it. Make sure you can do it. So yeah, V equals 3e to the 14 times 5e to the minus 7. This is something you can do in your head. I know I generally don't tell you, I tell you all don't do that. But this is, if you know how to combine scientific notation, this is something. When you multiply, you're adding those exponents. So e to the 14, e to the minus 7. When you add those together, you get e to the positive 7. 3 times 5 is 15. So this is 1.5 E8. This is simple enough math that you should be able to do without making a mistake. All right, great. That's the velocity. I didn't ask for velocity. I asked for n. So 3E8 divided by 1.5 E8. Yet again, this is something you could do in your head. These cancel. 3 divided by 1.5 is 2. Great. There you go. I'm not actually going to bother too much with Part B because Part B is a great problem for y'all to practice on your own. Part B, what you need to do is find the frequency. If you want to solve Part B, the first step is you need to find the frequency, and there's a rule that the frequency doesn't change no matter what material you're going in. No matter how fast you're going, no matter how fast light is quote-unquote traveling, frequency is the same. So you're going to find the frequency, and then in the vacuum, your speed is c. So if you have frequency and you have the speed of light, you can get the wavelength. I'll just kind of jot that up here. For Part B, find f, and then c equals f times lambda. And so that'll let you do that. But I'll let you practice that. It's good practice. If you're like, how do I find frequency? That's great practice. All right. This next slide is not going to be... Well, here. I'm going to kind of kick this later on so I can give you the rationale for why this is useful. So we're just going to kick this way later. It's harder to tell you why this matters now. All right. So the next thing I want to just show you is here's a bunch of index of refractions. Now, all of these are measured when the wavelength is 589 nanometers. It turns out that these change based on what material you're going through. We'll talk about that later. I'm not going to test you on it. I will always either give you the values of n or I'll say find them, solve for them. You do not need to have these memorized. If you need them, I'll tell them. And the value of n has to do with the properties of the material. It's really complicated. It's very often that the more dense your material is, the higher the n value is. But it is not always true. For example, I don't know. I'm just going to take some guesses here. Actually, I have no idea which of these are more dense or less dense. I'm just going to tell you that it's not a guarantee. This is actually a really complicated mechanism here. What these values of n are, how do they determine it then? Experiments. We're going to actually see an equation for how they determine these things. And in fact, that's your lab today. Your lab today is I'm going to give you a material, and you're going to find a value of n for that material. You're not going to be measuring the speed that light travels through it, just to clarify that. We don't have equipment sensitive enough for that. So I'm going to teach you, there's one more equation I need to teach you, and you're going to use that to find n. And this is very important. Why do we care about this value of n? Again, we got to get to the next equation for me to convey why. We'll do this question real quick, just to make sure you all can kind of see something here. How does the speed of light in water compare to the speed of light in glass? And be careful. This again, these kind of problems, make sure your answer makes sense. Make sure you can read these. And for example, this first answer says V water equals 0.85 V glass. The thing you all need to think about, does that mean that the velocity of water is faster or slower? Actually spend some time in thinking about what these answers say. Does answer say that water is faster? Does answer C say water is fast? You know, that's going to help you actually answer this question. So, try it out. It's a ratio problem. So is water faster water or slower? Plug in a number of boxes. Make a number. 15 boxes, 10. What do you want? Bigger or smaller? Small. 10 times 25. So as n goes down, should light go faster or slower? Take the extreme. That rules out actually. That's good. That's the way. Yeah, that's yeah. That's good.
The light's the same.
So which one? What should light travel fast? Smaller bit or bigger?
Oh yeah.
What's the smallest bit? To see what happens. You're really fast for science. So if you're happy with the beat, but he's going to be so maybe
what's fast? Yeah. So you let you catch I think I heard the sound first. It sounds fast.
Okay. I'm sorry. That would be
I like the ones that are like. What do you mean?
Yes, I do. All right, give y'all about 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so a really important skill I want us to make sure we're good with is to be able to read these and make. Okay, so before we read these and see if they make sense. So to that end, as n goes down, do I get faster or slower? And to answer that question, I'm going to remind you all of this problem, the one that we just did. When n is the smallest value possible, which is 1, am I going the fastest or the slowest? Fastest. As n goes down, v goes up. As n goes down, v goes up. So in which of these cases, which is the velocity faster, in water or in glass? Which has a smaller n? Water. So whatever answer I pick better match that logic. This is a useful kind of thing for checking your work. Now, this first expression, again, this is a skill that is very important to be able to look at this and say, this first one, what's bigger, V water or V glass? And if you're unsure, make up a number. If V glass was 1, what would the value be for V of water? You can do this, y'all. What's 1 times 0.85? So, does that match our logic? Is my water faster than glass? No. Without doing any math, I rule out these two answers because they don't obey the physics. They don't obey the concept that as n goes down, v goes up. This is really important to be able to read these answers and say which one's bigger and which one's smaller and how they compare and things like that. All right, so these are the only two that are viable. And the trick we're going to do here is, so n equals c over v. Rearrange this. C equals n times v. Why am I doing this? They both equal c. C equals n H2O, v H2O. C equals n glass times v glass. If A equals B and B equals C, they equal each other. I can set them equal to each other. That's generally kind of the trick to some of these problems when you're comparing things. You want to be able to set them equal to each other. And so then I just get the V of H2O equals the N of G over N of H2O times V of glass. And so that ends up being 1.55 divided by 1.33. And that's the 1.17. Really, this question was just determining which way do you divide it. Do you divide 1.55 by 1.33 or vice versa? And great, there you go. Cool. Okay. Great. And we did it. This is going to be a hand-wavy explanation for why light bends when it hits a different material. I have a stick traveling to the right, as shown below, down to the right. When that bottom of the stick hits the water, what's that going to cause the stick to do? It's going to cause the stick to slow down, but literally if this is happening, what's that stick going to physically do? It's going to bend. Oh my gosh, light does the same thing. This is such a hand-wavy explanation for why it does it, but it gets you the right answer, so it's useful, right? Now, again, why does light actually bend is a really complicated answer. It has to do with, as it goes in the material, the electrons vibrate, they make their own waves. The combination of these waves together results in a plane front that's angled. It's not an easy explanation, y'all. But yeah, you can do it with also showing waves, but the stick is the easiest way I've had to explain it. And it even matches. When you go from less dense to more dense, it bends in the same direction that a stick would. So it's great. Okay, here's Snell's law. It's a law. There's not much for me to tell you here as far. I don't derive this. This is experimentally measured. N1 sine theta 1 equals N2 sine theta 2. When light goes from one material to another, this expression tells you how it's going to bend. Both of these angles are measured with respect to the normal, that dotted line, the area vector. So theta 1 is where I start, theta 2 is where I end. Beginning equals end. So there you go. Light bends. This is very, very important for us. That's how you make lenses. You're like, why do I care about lenses? They're everywhere. Pretty much anytime anyone's doing anything with light, there's lenses involved. Your eyeball is a lens. Your camera's got a bunch of lenses on it. If you are messing with light, you're playing with lenses. And lenses bend light in a productive manner. We're actually not going to learn the equation for a lens, unfortunately, but whatever. You can do it on your own if you need it. It's easy. But this expression explains how light behaves when it goes from one material to another, which it's doing all the time. This is why, if you're looking, so something kind of interesting example of this, when there's like the ground is hot and it makes the air look all vibrating. Why? Because that hot air has a different index of refraction than the cold air. And so the light bends as it passes through that wavy air, and it makes it look all weird. Yeah.
Is it eyesight issues caused by your eye lenses being shaped?
Yeah, so this also explains your eyeball has an index of refraction. Again, you got a lens in it. If your lens is not able to bend the light sufficiently, then you are nearsighted like myself. If your eyeball is not able to bend the light enough to focus, the other way around. It bends it too much. If your eyes bend the light too much, then it focuses them before your sensors, and so you get a blurry image. If your eyes don't focus them enough, then you're farsighted, and it's focusing them behind your eyeball. We care about this bending thing. Another example of this, before we even do any, don't want to say this now. This also explains rainbows. Specifically, I need this in one more slide that I kind of skipped before. So this equation says how much it's going to bend. Now, N changes based on the wavelength of light, meaning it's going to bend different amounts depending on the wavelength of light going into it. So red light, green light, blue light, those are all just different wavelengths of light. And they bend different amounts because that's just index of refractions vary based on how much light bends. So because each one gets bent a different amount, when they go through glass, they get spread out. One bends more, one bends less, and you get a rainbow. Raindrop. When you see a real like a rainbow in the sky, that's because the water droplets are the light bends when it goes into it. It bends, hits the back of the raindrop, bounces out of the raindrop, and when it comes out, the light is now split, and you get a beautiful rainbow and all that jazz. So, yeah, using those two pieces of information, we now understand rainbows. Yay! Which is nice. We're not going to solve any rainbows. All right, but this equation is really easy to use. It's so easy to use, I'm not going to even like do one with, just like try it. I have the utmost confidence you all can solve this. What is the angle that light would refract into water? Refract is a fancy word for saying the angle it enters water with. It's going to be different than the angle I hit with. So I start in air, and I enter water. And just to remind you all, this is basically the only challenging thing here, is that all these angles are measured with respect to this dotted line. So it says I hit the surface, so I'm coming in with 60 degrees, and I'm asking you to find the angle it exits with. Start in a material, I end in another one. I start with some angle, I end with some angle. Find the angle I end with. You are very capable of doing this. This should be no problem. And this will be your lab. Except instead of, you'll measure the angle and you'll find it. Oh, sorry. Thank you. Y'all are good at that. Make sure your calculator's in degrees mode because the answers are all in degrees. I guess you do it in radian mode. You good?
Are you in degrees now? All right, give y'all about 20 more seconds or so. If you're not sure what to do, call us over. Ask people next to you.
For this.
No.
No, they didn't. Yeah, it's one of those, you do it enough, and I guess.
Okay, so long as you punch the numbers in.
5, 4, 3, 2, 2, 2. Alright, I'll leave it open. What? Alright, we write the equation, and then you plug numbers in and do algebra. Alright, well actually we're going to do the algebra and then plug numbers in, because that's the fastest way. Alright, what are we solving? Okay, first we should say what are we solving for? We're solving for theta 2. How do I find theta 2? We do some algebra, and we get sine inverse of n1 sine theta 1 over n2. Great, just plug in the numbers in. Sine inverse of 1 times sine of 60 over 1.33. You cannot do this in your head. There is no way. I can't. I don't know. I've met someone that can do sine it. I guess you get an approximation maybe, but if you didn't know this, the way your calculator does sine and stuff like that is actually, I believe, Taylor series and things like that. Something you may not have thought of, and you can only understand if you're taking Calc 2. Your calculator does not. I guess it could have a table, but I'm pretty sure it just does a Taylor series calculation. It has that function in there for like the first 3, 4, 5 terms, and that's how it does these things. All right, great. I'm not going to even do the next one because it's more the same and it's great, whatever. Last thing I need to teach you is it's using the same equation. N1 sine theta 1 equals N2 sine theta 2. What is the maximum value that theta 2 can be? When light goes from one material to another, there is a limit to what the angle can be. What is that limit? If you're unsure, draw a picture. Draw a picture of light going in. Remember what the angle is measured with respect to. Draw a picture. I normally am tempted to draw it for you, but no, I don't want it. I want you to draw it.
I think it's because I think if N1 and N2 are both 1, it's not good. And I can't inverse sine. So those are only defined from theta. What do y'all think? That might be.
Okay. Yeah, I was just
Because 0, 1.
taking the right hand side and just like putting it related to like theta.
Yeah.
Take that derivative, set that to 0. So cosine 0.
Yeah, that works. Yeah.
Good old calculator.
I'm pretty sure it's just the.
All right, give y'all 20 more seconds.
Girl.
What is your picture of?
Is it still in the material then? No.
It's not.
Theta 2, you have to be in the material for it to be theta 2. Otherwise, you're no longer refracting. You're reflecting, and reflecting doesn't follow this rule. Yep. All right, in 5, 4, 3, 2, 1. All right, to answer this question, I'm going to pull up a simulation that I really should have had open before anyway. I should have had a link to it, but whatever. We're going to go to FETs. FETs are awesome. I've been using them a bunch of times here, so FET, and I'm just going to type refraction, so if you want to find it, you can do it yourself. And this is to prove this this point. Now, for this to work, I need to actually, so here's a little simulation of this. You can like put your laser and, it refracts. I start in air, it goes into water, it's nice. I need to flip this though, because no matter what I do here, I don't actually reach the maximum angle. So let me actually switch this from water to flip the thing. So I'm going to start in water. I'm going to go into air. All right, and here's the point. Theta 2, if I put my little protractor over here, theta 2 is the angle measured with respect to this normal. So I rotate this, You can't get above 90. Why? Because you're no longer in the material. If you're like, what about this ray up here? That's reflection, not refraction. The angle I go in with equals the angle I exit with. It follows different rules. So, yeah, this is the whole point here. We have discovered total internal reflection. This is a very useful thing. If you want light to stay in a material, you use this property. You're like, why would I want light to stay in a material? Fiber optic cables is the easy example for you all. What is a fiber optic cable? It's a cable that makes light go through it. How do you make sure the light stays in the cable? Total internal reflection. You need it to keep bouncing. You can't just have it be absorbed by the walls, then it doesn't get to the end point. You need it to bounce in the inside of the cable until it reaches the end. We call this a waveguide because it guides the wave. So great, total internal reflection. It's when this equals 90. And then it's a super easy derivation. I'm not going to I'll just do this real quick. I'm just going to solve it instead of sending it out to y'all. So total internal reflection is exactly what we just found. When theta 2 equals 90, so N1 sine theta 1 equals N2 times 1. This special angle is called the critical angle. It's the angle at which this happens. And it ends up, if you just do the algebra, it's just N2 over N1 equals the special angle. We call this the critical angle, the angle at which the light no longer leaves the material. One practical application for this for you all, other than fiber optic cables, is say I was standing over here. I know you're like, what do you mean standing over here? This is upside down. Turn your head upside down and pretend like this is a pool and that someone, like there's a toy in the pool. If you are standing over here, you will not see the toy. You cannot. Why? Because the light from that toy cannot reach your eyeballs because it stays reflected in the pool. That's one of the applications here of this. At certain angles, you cannot see into the water because the light will not exit the water at those angles. So there's that. Last little other thing. So there you go. There's the derivation. Yay. I'm not going to actually ask a question on this in the test because I actually didn't get to it in my lecture class. So it's fine. But some practical application, fiber optic cables. One of the ones that's also kind of interesting is you all probably heard about the Ray-Ban glasses. Maybe not, maybe so. They're like the new hotness. They're these glasses that have a display on the glass. For there to be a display on the glass, they need to make light go through that glass and then bounce to certain places to go to your eyeball. How do they guide that light? Waveguides, total internal reflection. They make these pathways that the light bing, 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 bings on, and then it gets to a certain point and it reflects off a different material into your eyeball. And then it's as if there's an image there. Being able to control the direction that electromagnetic waves move in is useful. Not just for visible light, but also radio signals and things like that. Yeah, that's another example. Diamonds, they facet them such that the light bounces around a bunch of times and you get a nice pretty thing too. So, yeah, when you play around with the surfaces of things, you can make this stuff happen. But it's practical. It's useful. It's all over the place. You don't realize it. And they're called waveguides. They guide the waves through total internal reflection. And we did it, y'all. That is the end of the content for physics step. That's it. That is the last thing in this class. Yeah. We got a lab, but I am done teaching you new things. Unless you come ask me questions. Which is exciting. Now, clearly I haven't taught you everything there is to know out there, so, But for this class, I've taught you enough. Yeah, I didn't get to cover AC circuits. All right, so I'll end the broadcast at this point because we're just going to do the lab, but I don't know. Hopefully that's a cool feeling. Y'all learned so much. So many things. You all have learned enough to understand way more than 99% of people out there when it comes to electronics and things like that.